something here. You like writing the blackboard here, I think. Thank you so much. Good afternoon, Emre. Thank you so much. What about you? Good afternoon. Yes, I think we stayed the 16 slides here. I think you miss writing so much here. That's right. We do this example? Do you remember? Yes. Okay. And I gave you a homework. And I think we state that ionic radius. Did we do it here or not? I think not. Do you remember here? You write something. You don't need to send your homework. It's just only for you, Emre. Always I said that. Did we do that here? You said yes and no. I think I will do here. But before starting the lesson, okay. Before starting the lesson, I want to make a statement, and I will send you what I said here as an email. Please listen to me carefully, okay? Students who want to attend the lab course have to write a name for a student that I will choose here. For example, which one do that? For example, Bihter. Okay, Bihter always attend my lessons during my lessons. So you do a list and students who they want to attend the lab course, and I will make a schedule and set the day according to this situation. It is not necessary to come to the laboratory lesson, okay? Not necessary because of the pandemic situation, you know that. If you want, I will do it face to face in the laboratory. And I will upload all the videos of the experiments I have done in the laboratory to the system. And you can watch all of these but actually you have to watch, okay? You have to watch all of them and write your reports up to these videos, or if you come to the laboratory, you write here. Whether you come to the laboratory or not, it will not affect your grade, okay? Only the reports you write are important. Those who have taken this course and the previous semester will only need to watch videos, okay? Not need to come, and the others actually, and they will get reports. I can understand those who don't want to come to the laboratory because of this pandemic situation, because the situation is getting worse. Videos will be enough for you. I will send you what I said here, as I said, in the email. Okay, is that clear? Okay, I think this is clear. If you want to come, you can come according to you, to your number. I will make a schedule. Okay. Yes, let's start our lesson. Ionic radius. Ionic radius, for example, look at here. Minutes. Yes. Sodium and magnesium metal. These are not ionic. These are only metal, and they have no any charge. And because of their metals, they get positive charge. Okay, when a metal atom loses one or more electrons to form a positive ion, always the metals atom loses their electrons, and they getting cations. That means the positive ions. The positive nuclear charge exceeds the negative charge of the electrons in the resulting cation. And cations, these are the rules, and very important. Cations are smaller. That's radius. Smaller the atoms from which they are formed. Don't forget that. If you want to compare the atoms' atomic radius, you have to look their isoelectronic cations. What does it mean? Iso means the same electronic number, we can say. For isoelectronic cations, the more positive the ionic charge, the smaller the ionic radius, because they loses their electrons. You can think like that. This is the weight. Okay, if you lose your weight, you getting smaller, like these atoms. And you have to look their electronic numbers. If the electron numbers is the same, you can compare these atoms. Anions are larger than the atoms from which they are formed, because anions always getting the electrons and taking electrons and getting more and more larger. For isoelectronic ions, the more negative the charge, the larger the ionic radius. Don't forget that. Okay, this is important for comparing our ionic radius atom. Okay, and look at here. This is example of here. Refer only to the periodic table in the inside front cover, and for example, this is think about the periodic table, and arrange the following spaces in order of increasing this ionic radius. For example, you have to look their electron numbers first of all. So I have to give you these atoms proton numbers. Please, you can write here. And for example, for the potassium, the proton number is 19. I write here, this is 19. And then for the chlorine is the 17, and the discharge is negative. And then the sulfur proton number is 16. And then for the calcium, and calcium proton number will be 20. Yes. First of all, you have to check their electron numbers. Okay, you have to check that. For potassium, these electron numbers, what will be? Yes, that's right. This is the 18. Yes, and then for the, I am so sorry, this is not carbon, this is the chlorine. You don't say anything. Yes. For the chlorine, this is also, yes, 18. And then for the sulfur, this is again 18. And then the calcium, yes. All of these atoms electron number will be 18. Okay, you have to find first of all this electron number. And then these are isoelectronic ion. And you can compare these ionic radius. And you have to check their charge. First of all, you have to know that the anions always gain, always taking electrons and become larger. Which one? Chlorine and sulfur anions, because of this is the negative one and negative charge. Which one is the bigger? Chlorine or sulfur? Which one? Yes, sulfur is the biggest one. And then what's that? This is the chlorine. And then potassium or calcium. Which one is the bigger? Calcium or potassium? Which one? You know that cations always giving their electrons and loses their electrons, and potassium only one electrons giving, and calcium more than. This is the two. You will think like this is their weight, and potassium lose only one weight, and calcium loses two weight. So the potassium ionic radius is bigger than the calcium. Okay. Kelat, you said phosphor. Where it is? Yes. Is that clear? I think clear, because this is so simple example of these ionic radius. About ionic radius, I will pass this slide. I think clear or not clear? You say something? Okay, only for Nazar. Okay, this is your homework. I always said this homework only for you. You don't need to send to me. Okay, this homework only you work, you study. Yes, this is a comparison. Yes, a composition of some atomic ionic radium. Look at here. Just my hand. The values given in picometer. This is picometer, and these are all of these picometers are metallic radii for metals, for example, for that. Single covalent radii for non-metals here, and ionic radii for the ions indicated. And look at here, the lithium and beryllium for the beryllium metal. These are the only atom, and they have no any charge, and they get any charge here, the lithium and the beryllium. Look at here, this ionic radius is very smaller than which they are. And look at that one. You know that yes. Okay, I think I heard a sound. Okay, this is from up to the down. The radius become larger because of their radius, and because of what? Because of what? Their size getting larger. You know from the last lesson, last week. Yes. You say something. And look at here. having more electrons. And what else? Actually, one reason is very important than more electrons. These and that one, that become larger. Why? Because of their getting shells. This is the second, third, fourth, and fifth shell. So they have getting much more bigger. Yes, and the other one, lithium, beryllium, the same periodic table, the same periods. Look at here, becomes smaller again because the same periods, but they have get some more proton numbers, and the nucleum push their electrons much more. So the radius getting smaller from left to the right. Okay, I think that's clear. And the other subject is ionization energy. Ionization energy means, yes, Süleyman, you say something or this is wrong? Which are the atomic and which are the ionic radii? Okay, these are, if they have any charge like a lithium, beryllium, barium, carbon, like that, this is the atomic radii. But they have any charge, for example, +1 or -1, these are the ionic radii. Okay, for example, look at here, look at that one, the lithium atom. This is the 152. This is atomic radii. But this is the lithium positive charge, +1 charge. This is the ionic radii, is 59. Okay. What about the noble gases? Noble gases have so stable, so they don't need to any giving or taking electrons. So we don't need to compare their atomic radii. Okay? Because they are so stable. Let's do this ionization energy. Do you know that, or did you heard? Do you have any heard this about the ionization energy? Energy required to remove an electron. Yes, but these atoms must be a gaseous atom. Okay, must be a gaseous atom, and this atom must absorb to be able to expel an electron. The electron that is lost, the one that is most lose the health, and they have to appear any energy, and ionization energies decreases as atomic radii increase. Okay, if the atomic radii increases, the ionization energy decreases because the nuclei push the last shell's electrons weakly. Okay, because this is so far. So I can take their electron, the last shell, easily. So this ionization energy is so decreased, so low. Okay, and for the magnesium, look at here. This is the parenthesis. In the parenthesis, this is the G. That means the gases atom. Okay, that is very important for the gases atoms to take their electrons from the last shell, and this is the first ionization energy will be like that, and then the second ionization energy will be higher because you take the first electrons from the atoms. This is so hard to take electrons from their last shell. Look at here. This is also important. For that one here, the table, yes, here, this table, ionization energy of third period elements, okay? This is the same. Sodium, magnesium, aluminium, sodium, all of these atoms are the same periodic number. And they have, their radius is getting more smaller. You can think like that. And for the first ionization energy, check here, the sodium, for the sodium first ionization energy, look at this energy, okay, and then for the magnesium, this is the bigger one, okay, from the than the sodium, and then the aluminium, look at here, this ionization energy is lower than according to the magnesium, and the silicium, it is higher, and then phosphor, it's higher, and the sulfur is the lower than the phosphor, and chlorine and argon is so high because argon is noble gases and they are so stable. Look at all of these, ionization energy also so higher, and think about that. Why here? That's for the aluminium or for the here, and then for the phosphor and sulfur is like that. Why? Think about why that energy is not 1A, 2A, 3A like that. This is that means the 1A and 2, 3, 2, 4, 6, 5, 7, and 8. Why like that? I am waiting your answer. Why like that? Actually, this is the hint that's telling you why did arrangement like that. Actually, this tells you, this table tells you why. Actually, I said to you this answer last week. Yes. Beaters, thank you so much. Yes, that's right, because of the spherical symmetry. Spherical symmetry situation is very stable one, and if the atom is very stable, you cannot take an electron from it, because this is so stable and the energy will be so higher. Okay, and here, look at here, the magnesium atom, for the magnesium atom, these are the orbitals, and they have 2 electrons. This is the spherical symmetry, because of this is full of these orbitals. If you want to take that orbital from these orbitals, the electrons, the energy will be so higher. But for the aluminium, there is no any spherical symmetry, and in the p orbitals, they have only 1 electrons, and you can take easily these electrons from the aluminium. And then for the phosphor atom, these are the spherical symmetry also rule, because the spherical symmetry rules, that means the full of these orbitals or half of these orbitals. Okay, and this is the for these phosphor atoms, this is half of the orbitals, and you cannot take these electrons from these p orbitals, because spherical symmetry, and this is so stable. Okay, and that will energy will be so higher. But look at this sulfur. This is not any spherical symmetry, and this is not stable one, and you can take this electron from here easily. So this sulfur first ionization energy is smaller than the phosphor, and same thing, the aluminium ionization energy for the first ionization energy is smaller than the magnesium atom. That means the spherical symmetry. And look at here, this is the only the same, the third period, but here atomic ready and first ionization energies of the alkali metals. Look at here, lithium, sodium, potassium, rubidium, and cesium. All of these atoms are in the first A group. Okay, this is the 1A group, and they have much more getting their radius is higher, and then the ionization energy will be getting lower because the nucleus of atomic protons push their electron, the last shell not good pushing one. Okay, so you can take their electrons from the last shell, you can take easily. Okay, and the energy is very, very lower than the lithium. Is that clear? This is the comment about their these atoms ionization, only comments. Is that clear? Yes, for example, look at here. They ask us increasing first ionization energy for, this is arsenic, tin, bromine, and strontium. Which one? First of all, you have to sign these atoms and then comment. Okay, arsenic will be here, and then tin here. Yes, and bromine here, and strontium here. Yes, how do you do this example? First of all, you have to look which one. You have to look which one situation. This is that will be group or period or atomic radio. Please tell something about that. Bihter said group. Yes, we can say, but all of these, first of all, this is the 1A, 2A, is 3A, 4A, 5, 6, and 7A. Yes, this is 2, 4, 5, and 7. You can compare up to group. How can you compare that here? Actually, we know that the smaller first ionization energy is 1A and 3, and then 2, 4, 6, 5, 7, and 8. But don't forget that this arsenic and this bromine and the others, not the same periodic number. Not the same periodic number. This is the first, 2, third, fourth, fifth. That one. These are the fourth, and strontium and tin are the fifth period number. Yes. So, first of all, we have to compare that up to their periodic numbers. Strontium and tin atomic radius is bigger than the others. Okay, and their strontium and tin atomic radius is bigger than, not bigger, smaller than, okay, lower than arsenic and bromine. Why? Because of their atomic radius. If the atomic radius is bigger, the ionization is so lower. You know that. But if I want to compare that here and that one, here strontium and tin, which one is the smaller? Tin is the smaller. So the tin first ionization energy is higher than strontium. Okay, and we can write here like that. What about argon and bromine? Which one atomic radius is smaller than the other? Yes. Not is arsenic. Yes, that's right. Bromine. Which one? Arsenic. Yes. The bromine atomic radius is smaller than the others, and this first ionization energy is so higher than the arsenic, because this atomic radius is so smaller and the nuclei pull their electrons so strict, so powerful, okay, and you cannot take their electron from the brom easily. So this is first ionization energy so higher, and we can write here arsenic and bromine. Okay, is it clear? And this is your homework. You have to compare all of these. While comparing these atoms ionization energy, first ionization energy, please check your periodic table, okay? While looking periodic table, and then comment all of these atoms. The last subject of periodic table, electron affinity. Electron affinity, ionization energy, vice versa, I think we can say. The ionization energy is the energy change for the removal of an electron. You know that for the ionization energy. And for the electronic or electron affinity, we can write EA, can be defined as the enthalpy change. Okay, look at here, this is enthalpy change, and this occurs when an atom in gas phase. Okay, gas phase is very important, like ionization energy. Gains an electron according to this definition from the electron affinity of fluorine is a negative quantity. For example, look at here, for the fluorine atoms, for the gases, gains an electron and enthalpy changing will be like that. For the oxygen atom, gain an electron and the atomic electron affinity will be like that. But if you want to give an electron again, these electrons push each other, and the energy will be the positive one, positive enthalpy changing. Okay. Yes, that's it for the periodic table subject. Can you upload the answers later? Yes, okay. For that week's chemical compounds. Chemical compounds are very important because while you look a chemical formula, you should read this formula, or if you want to write any chemical formula, you can read it. Okay, you can read and you can write. This is very, very important. For example, yes. So, water or ammonia, carbon monoxide, carbon dioxide, all of these substances, all of these molecules are rather simple chemical compounds. You know that. How we can write the water? You know that the water will be, what's that? Will be, yes, all of you know that this is the water. This is not chemical rules, like not we write here the dihydrogen monoxide. We don't write here the water. Or ammonia. Ammonia formula. Yes, that's right. This is the ammonia formula. You don't write here mono nitrogen trihydrogen like that. Okay. Carbon monoxide, carbon dioxide, all of these chemical compounds, two or more atomic atoms come together and then give you a chemical compounds. And for example, less familiar are sucrose, for example, canned sugar, we can say acetyl salicylic acid, this is that is aspirin, and ascorbic acid, this is the vitamin C. They are two chemical compounds, and all of these acetyl salicylic acids and ascorbic acids and sucrose, all of they have carbon and hydrogen atoms, and we named all of these chemicals generally called, what are they? Carbon and hydrogen. Yes, that's right. This is the organic compounds, and the others that they have not any carbon atoms, they are, what's that? They are the anorganic chemical compounds, but except two molecular chemical compounds have carbon atoms, but they don't. They are not organic compounds. Do you know that? What are they? Do you know? They have carbon atoms. You know? No, Bihter. This is not. Yes, carbon monoxide is not organic compound. This is anorganic compounds, but it has carbon atoms. And what else? One more. Not glucose. Glucose, of course, organic compound. You're right. Yes, that's right, Bihter. Thank you so much. This is carbon dioxide. Carbon dioxide also is anorganic compound. It is not the organic compound, although it has carbon atom. Yes. Look here, types of chemical compounds and their formulas. Generally, speaking, two fundamental kinds of chemical bonds hold together all the atoms in a compound. Covalent bonds, that means involve a sharing of electrons between atoms. Okay, sharing of electrons, that's we can call that covalent bonds, and give rise to molecular compounds. Okay, don't forget that. If the molecular compound has the covalent bonds, that means this is the molecular compounds, and generally these molecular compounds will be between ametal atoms. Okay, and ionic bonds, this is involves a transfer of electron from one to the another, and they give us ionic compounds. And generally this is that will be happen between metal and non-metal atoms. Okay, and this is called ionic compounds, and the others, and metal, non-metal and non-metal means that is molecular compounds. Don't forget that. This is very important while naming the molecular compounds, while writing the molecular compounds or ionic compounds. Yes, first molecular compounds. Here they give us a formula for the water. Here, yes, for the water, the constituent elements are denoted by their symbols here, hydrogen and oxygen. The relative numbers of atoms are indicated by subscripts here. That means the hydrogen involves which one? 2, and oxygen, that means there is any number of the subscripts, that means the only 1. Okay, don't forget that. For example, carbon tetrachloride here, if we can write here, for example, look at here, that is represents the compound carbon tetrachloride. The formulas and both represent distinct entitized molecules. So we can refer to the water and carbon tetrachloride as molecular compounds, because carbon and chlorine is the non-metal, and hydrogen and oxygen is the non-metal. So they have the covalent bonds also, and these are called molecular compounds. Don't forget that. And when we are reading this formula, carbon tetrachloride. Okay, and also I will do some example, and you learned how you write and how you're reading these compounds. Don't worry. And these are the some terms, and these terms important. For the empirical formula, the empirical formula is not the real compound. Okay, it's not for example, subscripts very important for the empirical formula. Subscripts in an empirical formula are reduced to their simplest whole number ratio. For example, here P4 and O10, you can simplest this whole number ratio, the subscripts, and you can divide it to all of 4 and 10. That means the P2O5, O5, and this is not the real compound. Okay, this is not the real compound. This is the empirical formula. And this is the molecular formula. This is the based on an actual molecule formula. And in other cases, the molecular formula is multiple of the empirical formula. A molecule of acetic acid, for example, consists of 8 atoms, 2 carbon atoms, 4 hydrogen atoms, 2 oxygen atoms, and this is for molecular formula of acetic acid is like that. Okay, here like that's carbon 2, hydrogen 4, and oxygen 2. And you can, if you want to write this molecular formulas of empirical formula, you have to divide it 2. Okay, and that will be empirical formula will be CH2 and O. Generally, the empirical formula does not tell us a great deal about a compound. Don't forget that. And the other term, this is a structure formula, and structure formula shows the atoms are bonded together in a molecule, and by what types of bonds. For example, covalent bonds or ionic bonds, and which atoms bonded with the other one. And this structure formula, for example, acetic acid tell us that three of the 4 hydrogen atoms are bonded to the other carbon atoms. Look at here, you will understand easily this picture. For example, yes, this is the empirical formula for that one. Okay, this is molecular formula for here, and structure formula. They have a bond, lots of bonds, and for example, for that molecular formula, they have 2 carbon atoms, and these are, for example, the first carbon atoms bonded with the 3 hydrogen atoms, and the second carbon atoms bonded with the oxygen, but the one oxygen bonded the double bond, and the other only single bond. And this is the structure formula, and we show these elements like a ball, and these balls tell us some elements, and they have some color. For example, the hydrogen generally shows the white balls, and the oxygen shows the red balls, and the carbon atoms show the carbon atoms. Don't forget that these are the important thing, and molecular model, we can say, ball and stick here. These are the stick. There are so much stick here, and then the ball, and the others, this is not any bondant. This is the molecular model, space filling, we can say. And we have some organic compounds here. For example, butane. Butane have 4 carbon atoms, and the others, all of these atoms will be hydrogen atom, and the balls structure like that. And the methyl propane will be like that. This is the actually 4 carbon atoms, but the last carbon atoms will be center of the carbon atoms bonded, and then that structural formula will be the ball structure formula will be like that. And the last one, testosterone hormone molecule, they have it has the oxygen atom also. You will look here, the red ball show you the oxygen atom. And the others, this is this color scheme for use in molecular models, and you should know that, for example, hydrogen, carbon, nitrogen, phosphor, iodide, This is the bromine will be, okay, this is the Br. Chlorine, sulfur, oxygen, fluorine is very, very important, and you know that. You need to know that. Don't forget here. And here, the size of atoms, the radius, okay, radius atoms reflected in the various size of the colored spheres are related to their location of the elements in the periodic table. So, for example, iodide is very, very bigger because this is the last periods of the periodic table. Yes, let's looking ionic compounds. Ionic compounds, you know that the chemical compound, the chemical combination will be a metal and non-metal. Usually results in an ionic compound, and the atoms or metallic elements tend to lose or one or more electrons when they combine with non-metal atoms, and the non-metal atoms tend to gain one or more electrons. As a result of this electron transferring, the metal atom becomes a positive ion, or we can call that this is a cation. And the non-metal atom becomes a negative ion, or we can call that this is the anion, in the formation of sodium chloride. Look at here, sodium chloride. This is the ordinary table salt. Salt table, you know that. Each sodium atom gives up one electron to become sodium ion, and then each chlorine atoms gain one electron from the sodium atom and to become a chlorine ion. This fact conforms to the relationship between locations of the elements in the periodic table and the charges on their simple ion. Don't forget that this is very important to reading and writing their named. Yes, this is the mole concepts and chemical compounds. You don't forget that. For example, for the molecular compounds, molecular mass, we can say, always I will give you atomic mass, okay? Always I will give you atomic mass. For example, for the water, the hydrogen atomic mass will be only 1 ATB, we can say, or we can say 1 gram divided mole. Okay, always we can write, we write here gram divided mole. They write the AKB or U, they say it, or AKB or U. And for the oxygen, this is 16 gram divided mole. If you want to find the molecular mass, you have to look at this compound. How many hydrogen in here? This is 2 hydrogen. 2 hydrogen multiply with it is atomic mass. What is that? This is the 1. And then collect the other atoms. Which one? This is the oxygen. Oxygen atomic mass, what is that? This is the 16. And how many oxygen here? This is the only 1. If you calculate this, this is the 18 gram divided mole molecular mass of water. For the magnesium chloride, this is the same. I have to give you these atomic mass one by one. This is magnesium, this is 24, and for the chlorine, this is the 35.5 gram divided mole. This is the same gram divided mole, and the magnesium only 1 magnesium has magnesium chloride molecular formula is only 1 magnesium, multiply with the it is atomic mass, and then collect the other chlorine. chlorine has 2 multiplied with the 35.5. Okay, you will find easily this molecular compound, 95 gram divided mole. What about this magnesium nitrate here? The nitrogen atom have 14 and the oxygen 16 and the magnesium 24. What about that? Do you have any idea? Magnesium nitrate. What about this? It is molecular mass. You write. Yes, you write here. This is not 60, I think, Bihter. This is 6 oxygen means. That's right. I think that's right. What about the others? Do you think anything about that? This is only 1 magnesium. Yes, multiply with its atomic mass. And then for that nitrogen, yes, for the nitrogen, here for the nitrate, it has only 1 nitrogen, but this is the parenthesis, and that there is a 2. That means this is 1 and 2 multiply with each other, and that means 2 nitrogen atoms, and you will multiply with the 14. And then what about the oxygen? That will be 3, but here the 2 multiply with each other, and this is the 6 oxygen atom will be, and multiply with its atomic number and calculate. That's it. Is that clear? Only I do these lessons with the Bihter. The others, I think this is clear, and this is so easy. Mole of a compound. Actually, this is very, very important, because the other example or problems, we will do lots of mole problems, and we will use moles. So this is so important, and the molar mass is the mass of 1 mole of compound, 1 mole of molecules of a molecular compound, and 1 mole of formula units of an ionic compound. What does it mean? For example, the water. The water molecular mass or weight, we can say, this is 18 gram divided mole. What does it mean? The units brim, the units tells us actually what does it mean? That means 1 mole water has 18 gram. Okay? That means the 1 mole water has 18 gram. And always this water has Avogadro numbers. What is that? This is the 6.02 multiplied with 1023 molecules of water. Okay? All of these 4 molecule will be like that. This is 1 mole, always Avogadro numbers equal. 1 mole equal with the Avogadro numbers. All of, for example, for ammonia, for water, for carbon dioxide, for all of these molecules has the same. 1 mole means is equal to Avogadro numbers. And here, downstream, molar mass and Avogadro constant. Density, you know that from the last lessons. D, this is the converse from volume to the mass, because this is the gram divided milliliter. And molar mass, this is the M, converts from mass to the amount mole, you know that. And the Avogadro constant, this is the mole to elementary entities, and this is very, very important thing while calculating our problems. For example, look at here. Look at that example. Analytical balance can detect a mass of 0.1 milligram. How many ions? How many ions? Okay. How many ions are present in this minimally detectable quantity of magnesium chloride? Okay. So first of all, if you want to find the ions, you know the Avogadro numbers and you know the moles because of the Avogadro numbers. If you want to mole, you have to know that this mass, okay, this molecule mass. What is that? This is the mass of the magnesium chloride, but this is the milligram. But you have to convert that for the gram. So if you want to convert this milligram from milligram to the gram, you have to divide that 1000, and that means the 0.1 multiply 10 negative 3. This is the gram, and then you have to convert that. What is that? You have to convert that from gram to the mole, because you have to you want to find the ions and you want to find the Avogadro numbers. Avogadro numbers means the molecules, but they want to give us they want to us this is ions. And here actually you know that this is the M is equal M, and this is the molecular weight, and this is the mole, you know, and this is the mass, and this is the molecular mass. Okay, molecular mass. You note this molecular mass from the last example. This is the 95 gram divided mole. If you want to find, if you want to use that formula, you can use. But this is so easy to use that unit. That means the 1 mole has 95 gram, but here we have 0.1 multiplied with that gram. How many mole we have? Okay, or this is the first way and this is the second way. So you don't know the mole, but you know mass. This is the 0.1 multiply 10 negative 3, this is the gram, and you know the molecular mass 95 gram divided mole. If you want to use that formula, you can use, or you can use this proportion. Okay, please can you find here, please calculate that and write the chat. Yes, I'm waiting. What is that? Please. Yes, you will do, you will divide this mass and this here. Yes, you will find the mole. What is that? Anybody? Yes, I had to calculate here. Anybody don't anything. Don't do anything. Yes, 1.05. 1.05 multiply, not 3, this is the 6 mole. Okay, and then this is the mole, and you have to pass from here to the molecules. Okay, you know that one mole magnesium chloride has, this is 6.02 multiply that Avogadro numbers molecule, but you have that magnesium chloride mole that like that. This is 1.05 multiply how many molecule you have. Okay, how many molecule you have to multiply here. Yes, here is that true? Yes, 6.33 multiply with not negative. This is the positive one, and this is the 18 molecule. But here we have 6.33 multiply with 10, 18 molecule. But this is the magnesium chloride molecule. Okay, but they ask us how many ions. The magnesium chloride, how many ions they have? It has, this is the 3. So you have to multiply it here with 3. Okay, and if you multiply with the 3, that means the 1.9 multiply ions, and this is approximately, we can write here 2 multiply with that ions. Okay, is that clear or not clear? Okay, this is the last, and then I will finish. Yes, this is your homework, and we stay here. We will continue from here to the next week. And Bihter, do you understand me? You will do a list to come to the laboratory who wants to come. This is not necessary. Okay. Okay. Yes, any question about that? Any question about that subject? Okay. So next week we will see you. Yes, Bihter, yes. You need to send, because according to the list, I will do the schedule. Okay, see you next week. Take care of yourself.